I'd like to introduce Rick Hudson, who's joining us today from Intel's Programming Systems Lab. He's been working for a number of years on memory models, and he has recently helped to put out a white paper clearly describing Intel's memory ordering. And today he's going to talk about that and what some of the motivations were behind the currently defined model. So, welcome.
Thank you. So I'm Rick Hudson. I'm from Intel. Just to get this out of the way, a bunch of names up at the top are the people at Intel who worked closely with me on getting this done. I won't go through all the names, but there they are. But I think more than that, there's also all the major language and OS efforts around the country were involved in reviewing this work. So this isn't something that came out of Intel without lots of close looking by the people from C and the people by Java and the people by Linux. And they provided general encouragement and support. And we really do appreciate all the work that they did also. So we needed to address some of the problems that were out there. And the current memory model that we would publish didn't seem sufficient. And in particular, type safety had to be addressed in languages like Java, and in particular, this thing called publication safety. And I'll show you in a couple slides exactly what that is and how we dealt with it. We had to support this concept of sequential consistency, which is really a high-level language requirement for a subset of program, in particular those things known as race-free programs, where race freedom is a dynamic property that, just to bring everybody to a level thing, we think race freedom is defined as multiple accesses at the same location where one or more of the accesses is a right. And again, that's a dynamic property as opposed to a static property. I don't want to really misdefine what Lambert defined as sequential consistency, so I put the actual definition on the board there. And if you don't know what that is, you probably actually do, because it's what you intuitively think a computer does. Okay, and so that's why people like talking about sequential consistency, because it's intuitively what the first person that comes to a computer, what they expect. One of the other problems, yes?
Why is sequential consistency a necessary condition for race-free programs?
Why is sequential consistency is okay, what happens is in Java and C#, what they're really saying is if you have a race-free program, okay, we will give you a sequentially consistent execution. That's really all they're saying. It's not saying that you need sequential consistency. All Java is saying is if you are race-free, you'll be sequentially consistent. Okay. Another problem we had to deal with was legacy, and Intel legacy is not only hardware but software out there. So we had to make sure that Linux didn't break, Java didn't break, so we couldn't change the memory model such that these programs broke. So a lot of time was spent looking at legacy code in this project. And there was a lot of motivation in the Programming Systems Lab to provide a solid foundation on which to build higher level concurrency constructs. And by higher level concurrency constructs, I mean like these obstruction-free DIM algorithms, transactional memory, any number of other types of concurrency constructs that people are starting to now develop as multi-core starts to happen, or many-core. Okay, so let's just dig right in here. So how are we changing processor ordering, which is the name of our model? We actually are making it more specific. And the ways that we're making it more specific is introducing this concept of TLO plus CC. And TLO stands for total lock order. And so the instructions with a lock prefix, these are things like an exchange or a lock compare exchange or fetch and add type of instructions. All of those will have a total ordering across all processors. And then we also added something called causal consistency. Okay, and this basically says that write visibility is transitive. Okay, so if I see something and you see, if I write something and you see it, and you write something and somebody else sees what you write, then they'll also see what I wrote. We managed to get this thing down into 8 carefully crafted principles. And if you understand these 8 principles, we're confident that you can go ahead and move forward and understand exactly what's going on in the x86 memory model. This talk and these principles are actually limited to write-back memory, WB memory, which is typically what people get when they, not typically, but what they always get when they do a malloc in C or do a new in a language like Java or C#. We're also assuming that accesses are naturally aligned, which means that if you've got an 8-byte load, it's aligned on an 8-byte boundary. This is not a difficult thing for compilers to deal with, and that's our primary target here. And it does not speak to some of the non-temporal instructions like the move NTI, which very few people use, but they're mostly used for video cards and DMA stuff. It also doesn't speak to other memory types like WCKs or write combining. So those will have their own rules, and these principles won't apply. But these are the principles that people that use malloc and stuff will be using. So what Intel wanted to do was we wanted a memory model that was as strong as required. And by required, we mean the legacy issue and required to move forward in a multi-core world. But we didn't want it any stronger because we wanted to preserve for our hardware, our architects, the ability to do efficient implementations. Okay, so high-level language, and then we also noted the high-level languages and compiler optimizations often obscure these differences. So if you hoist something out of a loop, well, the compiler basically is getting rid of the, any hopes for sequential consistency and so forth. We also were curious if there was any code out there that was depending on TSO, but not TLO plus CC. And we couldn't find any. I think that obviously there's a difference in the 2 models, but we couldn't find any active code out there that actually took advantage of that difference. I think you could probably write code that detects it, but nobody really has a serious use. No one seems to have come up with a use for that that's commercially viable. TSO is total store order. That's what SunSpark uses. Sequential consistency, or SC, is what Lamport originally defined and what most people think. And then we're TLO plus CC. So if we implemented SC or TSO, then we'd also meet our, all the requirements of TLO plus CC. So this implementation or that implementation will be compatible with the TLO plus CC. Okay.
Can you briefly mention what the differences are?
Sequential consistency we defined in the previous slide or a couple slides ago. That means that every load and store appears in program order, where program order is what's running on one processor. And all of the stores and there's some interleaving that everybody agrees upon. If you think about sequential consistency as what an old mainframe would give you, where you just swap threads and you executed all of the reads and writes in a single thread in order, you'd get sequential consistency. Total store order is, for most stores, all the processors will agree on what it is. If you may disagree in the ordering of stores with total store order between stores that you make and stores that other processors make. If you're familiar with what a store buffer is, this is typically called store buffer forwarding, is what breaks the total. It's the exception to total store order that you might find in a TSO. And TLO plus CC is what I'll talk about in a few seconds. So those are basically the differences between the 3 different models. And as you can see, since this order is both loads and stores, and this order is just stores, then obviously this is a subset of that. And since we only require causal consistency, that's trivially supplied by a TSO implementation since everybody agrees on all store orders. Okay, so here are the 8 principles. I wouldn't advise you reading them. I just wanted to show that we could put them on one slide. And if you can sort of figure out what's going on here, that's all you need to know. We're going to go over the 8 principles, and we'll stop along the way to discuss particular problems and try and give you some motivations on why that principle is there and why it's worded the way it is and what you can do with it. So these slides are going to be mostly given the 8 principles. The next 8 slides will give the 8 principles one at a time on each slide, and they'll give you an example of some code. And for those of you who aren't familiar with our assembly language, the way you read these things is you replace the comma with the word from, and then it'll read pretty well. So it's basically move 2x from constant 1. Okay, so
Destination source.
Yeah, destination source. Okay, so replace comma with from, and that's what I do, and it seems to work. We did it this way instead of putting the pseudocode C code up there because we wanted to really impress upon you that the compiler is not involved here. Okay, if the compiler does something like reorder those 2 things, you know, that's fair, and the compiler can do that, and we're not going to fix the compilers in the hardware. Okay. In these examples, initially the memory values are all set to 1 and the registers are all set to 1. If there's an R in front of something like there is over here, that means it's a local register. Okay, so we just pull in something from memory typically into a local register. If you see these brackets around something, then that's the location of the value inside of the location X. Loads cannot be reordered with other loads, and here's an example where processor 0 is doing 2 stores, okay, and I'm sorry, processor 1 is doing the loads, and processor 0 is doing the stores. So processor 0 is storing 1s in X and Y, and processor 1 is reading them from X and Y. Then neither processor 0 or processor 1 can reorder their accesses. So this means that if R1 is 1, which means that this Y here is seen by processor 1, this store here, then it will also see the store from processor 0. Okay, and you can flip it around if you want to do, if R2 is 1, then R1 can't be 0 either. So you can't really have the loads can't be reordered with other loads with. What?
Sorry, no.
Hundreds of people have looked at these examples. Okay, so the third principle is that stores are not reordered with older loads. Okay, so if you load something, then you store something, the store can't be reordered. Okay, so in this situation, R1 and R2 both can't be 1 because if processor 0 sees the 1, then that means that this move has already happened. Okay, and if this move has already happened, then the load above it has already happened. And if the load above it has already happened, then the store over here has not happened. So if you end up having to have either processor 1 happening before processor 2, or at least the store and the load, and that forces the other one not to happen. Now this is important, and we'll actually get to why this is important. But if one of the legacy things that we were working on was how to build critical sections, and Just sort of keep this in mind for a little bit, and we'll get back to it in about 10 slides. Now, we do allow loads to be reordered with older stores to the same location, to different locations, I apologize, but not to the same location, right? So one can see, in this case, if we're allowing these two loads to be reordered above the two writes, then obviously they can both see 0. Okay, so that actually is allowed by the memory model. If you want to prevent this from happening, memfence is the instruction you want to insert between the store and the load, and that will suppress this behavior. Okay. Okay, so here's where we're starting to diverge a little bit from what classically was part of processor ordering until this paper came out, okay? And this is one of the ways that we've actually strengthened processor ordering. We didn't really, strengthened isn't the right word, clarified, I think, is the correct term here. So in a multiprocessor system, and by processors we really mean just hardware threads, either whether that's a hyperthread or whether that's a core, they all sort of fall in the same. We're going to use all word processor interchangeably with those things. Think hardware thread. So what this says is if I write 1 to X, okay, and on processor 0, and processor 1 sees that for any reason, and then it writes 1 to Y, and then processor 2 sees what processor 1 has written, then by virtue of the fact that processor 1 has seen what 0 has, that processor 2 will also see the write of X, which means that processor 1 sees the 1, and processor 2 sees the 1 written by processor 1, then he cannot see 0. He will have to see the 1 that was written. So this seems like an odd thing to require in a memory model, but let me show you why this is critically important to building systems. So there's this thing called publication safety, which is really sort of a subset of type safety that we're going to talk about here. So assume we have each of these boxes are processor 0, processor 1, and processor 2. Assume you malloc up or new up an object in processor 0, and you set its vtable to something valid. And then you publish it, and this is where the term comes from. By publishing, you place it inside of a globally accessible location. In this case, I'll call it slow train. Okay, and then sometime later, this arrives, the value of slow train arrives at processor 1, and he stores that in something called warp drive. Okay, so obviously warp drive is named to indicate that it might get someplace faster than the slow train. And sure enough, if warp drive comes down here and gets here faster than the bits that were done by processor 0, then warp drive might try to execute a method. It'll dereference the vtable, and well, oops, things aren't good. Okay, so we have to make sure that, so that rule is here to make sure that if anything from processor 0 can make it to processor 3, then everything will make it. Okay, everything before that will make it. If it didn't, then you'd have this problem. So that's publication safety, and that's exactly why we put this rule in, is to support high-level languages that require type safety. So moving on to the 6 of the 8, this is pretty straightforward. Stores to the same location have a total ordering. So if you see, we're writing to X here, in processor 0, and then we're writing another value in processor 1. And all the processors in the system have to agree on the order that that's written in. For example, if processor 2 here sees 1, 2, which is 0, 1, then processor 3 has to see the same order 1, 2. It cannot see order 2, 1. Now, obviously, if this wasn't the case, you'd have a weaker model, for one. Such models have been proposed, but the real problem is that if you can't ever agree on what the value of x is, you're just not going to get understandable programs. Okay, so that's why we have this rule, and that's it. Okay, so lock instructions. So we're now declaring that locked instructions have a total ordering. An exchange is a lock instruction, and you can think about this just storing values into, well, exchanging whatever is in registers with the locations. So it's part of it's a store and part of it's a load. And so what we're saying is that if you're using lock instructions and you can detect the ordering between processor 0 and processor 1, if processor 2 sees one of these orderings, then processor 3 will see all similar orderings. We'll see the same ordering. So in this case, if processor 3 here sees 1, 0, which is going to be processor 0, processor 1, then it can't be the case that this guy sees processor 1 right before processor 0. So why do we need this total ordering? Okay, so we need the total ordering for a couple reasons. The really strong reason is that sequential consistency is in fact a high-level language requirement. Java requires sequential consistency for some of its constructs, in particular their critical sections, their synchronized statements, as well as their volatiles. And it's also required by serialization as a requirement for transactional memory. So that's one of the things you want with transactional memory, is to be able to have a total ordering on the transactions as they're executing. And so this is how you get a total ordering on our processors. You use a lock instruction. So to make the lock instructions useful in these contexts, we also say that loads and stores cannot be reordered with lock instructions. So in the case of processor 0, we have a lock instruction that writes something into, writes a 1 actually, into location X, and then we'll read from Y. And over here, we're writing a 1 into Y, and we're reading from X. So they're flipped. So the situation where R2 equals 0 and R4 equals 0 isn't allowed because one of these things had to happen first. Okay, and you have to agree. All processors will agree on which exchange happened first. Right. So if you want to use volatiles and you want to have this total ordering, okay, then you can use an exchange instruction to do that in your higher level language. And you'll get sequential consistency. So now you've seen the principles, and if you're not asleep yet, we'll show you how you can use these principles, an example of using these principles to reason about how one might build a critical section for a language like Java or something. In particular, we're going to use these 4 principles to build a critical section that has a specific semantic, and then we'll talk about how we might use some of the other principles to change those semantics slightly. So we'll go over how these things are used. Okay, so on our left, we have sort of a C type of scenario for critical sections. Lock acquire, some monitor, and then a lock release down below. And inside, we're going to do a load as well as a write, just so we can show you the interesting things. And over here, we have sort of how this will translate into assembly language, the x86 assembly language. So I'm not sure what lock instruction you want to use to acquire the lock. Some people use fetch and add, other people use compare and swap, but it's, whatever algorithm you're using, we can use. So loads and stores are not reordered with lock instruction. This is principle 8. Okay, so that means that this load over here, this move to R1 from location X, can't move up above the critical section. Okay, so you can't get out, loads can't get out of the top of the critical section. Okay. Also, it also talks about stores, and now that store also can't get outside above the critical section. So we've used this principle 8 to ensure that nothing can move above the lock acquire or the monitor enter, if you will. So let's now talk about not escaping out of the bottom of a critical section. One of the legacy issues that we ran into is that people were using a simple store instruction to release a lock. Okay, so there wasn't a situation where you had a lock instruction at the top and a lock instruction at the bottom. Several Java systems, including our own, were actually using a simple move of 0 into that. So we have to prevent things from escaping out of the bottom. The other way to look at that is you can't let the release move up into the critical section. That's sort of the flip of that. And principle 2 says stores are not reordered with other stores. You have 2 stores that can't be reordered. So we know stores can't drop out of the bottom of the critical section. Okay, so now we got 3 of the problems solved. And finally, we also have this principle that stores are not reordered with other loads. So in this case, we can't, the load also can't escape out of the bottom of the critical section. So this is how you would build a critical section using our memory model. This is how most Java systems have built critical sections, and this is what we're recommending. So we built a certain type of critical section here, and I'm sorry. The one final thing that some of these languages require is that these critical sections be sequentially consistent or have a total ordering. And here we use this final principle 7 that says that lock instructions have a total ordering. So in order to enter a critical section, we always have a lock instruction, and we're going to use that to always have a total ordering. And if you think about it a little bit, you'll realize that the release, if someone else is going to enter a critical section, they're going to do it with a lock instruction. So you can tie together the release and the lock instruction. And with a little work, I'm sure you can come up with a proof that says that the critical sections are actually sequentially consistent. Oh, yeah, right. Cool. So we've got this critical section. Loads can't get out. But what about the problem where we know that loads can pass stores? Okay, so it's possible that loads can get into the critical section. Okay, so you enter a critical section, you exit a critical section, you do a load. There's nothing to prevent that load from going inside of the critical section. That seems to be a perfectly reasonable semantic. We typically call it a Roach Motel semantic. The reason being that loads can check in, but they can't check out. Okay, so grad students seem to understand that better than people that actually have jobs. So anyway, what if we want to prevent? What if we want a semantics where loads can't check in? Okay, or get into the critical section. In that case, you would want to use an mfence, which would suppress the final store of the critical section with the loads that follow it. So that basically is the heart of my talk. Is you've seen the principles, and you've now seen how to implement critical sections with them. And so the other thing that we had, other problem we talked about earlier, was that legacy software and legacy hardware had to be honored. We spent a lot of time looking at our old processors, okay, and looking at our old systems, and making sure that they all agreed to what was in the white paper. If you'll notice, the white paper doesn't talk about M fences because they actually weren't available on the Pentium, so we didn't talk about them. We're not trying to hide what they do. It's just that the rules of the game was see if you can get a white paper that goes back to the Pentium. And also a lot of time was spent not only by us, but by the friends at Linux and the people at Microsoft and the Java memory model people, of which Jeremy was a member of, trying to understand what they actually use now, what kind of assumptions they've made over the years about our memory models. Sometimes they were overly cautious. For example, they were sticking S fences in when they actually didn't need them. It didn't hurt anything, but it slowed down their programs. And so now that there's a clear explanation that stores can't pass stores, maybe some of their code will get faster. So one of the motivations here was we felt if people knew what was going on, they could write faster code. Other feedback we got back, besides the fact that they wanted to release locks without a locked instruction, was that volatile reads had to be efficient, but they really didn't care about volatile writes. And if you look at, say, the Java concurrent util programs, they take advantage of this. So our volatile reads can be done with a simple load instruction, and our volatile writes can be done with an exchange instruction or any locked instruction. So we think we were successful. This was a multi-year effort by multiple people to get this out. They look complicated, but in fact, this is probably the simplest explanation of memory models that most people have ever seen. Okay, we spent a lot of time trying to break this down so people can understand what our memory model is doing. We feel that TLO plus CC is a solid foundation for building higher level concurrency constructs, and now I can get on to doing what I really want to do, which is building these constructs, now that I have a solid foundation beneath me. We did it in 10 pages, and there were a lot of spaces in those pages, and in a few slides, I guess we did 25 slides, okay? It's available as an Intel white paper if you have access to a search engine. Just type Intel memory ordering, and it should be the #1 hit. It says Intel 64 architecture, but that's the x86 as opposed to the IPF system. So this white paper is available, and it's being moved right now into the public reference manuals, and that's due to come out any day now. And you'll see the white paper actually being moved, nothing more, nothing less, into the actual reference manual. So what we're doing is we're putting white papers out now, and then by and by we're going to put the stuff into the reference manuals. That's it. I guess I have to show you this, but you don't want to read it. It's just an eye chart. I had to sign something similar when I came in, so I'll force you guys to look at it. And I guess I'll take some questions now from the audience.
What's the difference between an L fence and an S fence under this model?
Difference between an L fence and an S fence. Well, they're both no-ops in a write-back memory. So I guess none. Their intent is very specific. An L fence separates loads from other loads, and an S fence separates stores from other stores. But as you've seen, for write-back memory, okay, not write combining memory, some of the other memory types we have where L fence and S fence actually are important, okay, since loads are already ordered, sticking an L fence between them won't do anything. And since stores are already ordered, sticking a S fence between two stores also won't have any effect. Okay, so if you malloc something, you find yourself putting S fences and L fences, you need to reread the paper. Okay, if you're mucking around in the middle of some kernel code someplace, you might see some of this. Okay, and that was one of the reasons why we came out with this, because we really did feel that we needed to get a memory model out that didn't have these S fences and L fences, and they do cost, because they do start flushing stuff. Okay.
They are necessary for non-write-back memory, though.
They are necessary for non-write-back memory, and they're also necessary for non-temporal instructions that are operating on write-back memory, like the move NTQI or whatever.
So the model seems fairly reasonable, except for the item 7, which is the controversial one of having the total order of lock operations. Now, you do not provide any kind of a cheaper lock operation, nor do you provide any cheap way of doing, say, atomic updates without having a total order of all of those instructions. So, is that something that you would look at in the future to provide, faster or more lightweight synchronization primitives for languages like C++, which often do not need the strong guarantees?
Well, ideally, all we'd want to do is make the instruction with the richer semantic as fast as need be. Okay, and the jury's out on on how fast we can make these the lock instructions. Can we get them down to a tolerable speed? Okay, so this isn't, obviously you're asking for a semantic that's weaker than what we already offer. And the only reason you're asking for that, I would think, would be for performance reasons.
Yes.
Okay, so your complaint is really that the lock instructions aren't fast enough. Point taken. We will work to make them faster. The solution of adding, I mean, if you look at adding ISA as adding legacy, okay, then there's really a strong resistance, let's put it that way, against adding instructions until we've exhausted all possibilities of speeding up the instructions we already have. So I don't think we're against changing our ISA, but that's not in the plans that I know of right now.
Okay, so my concern is twofold. One is that the lock instructions currently are very slow, and item 7 makes every lock instruction dependent on every other lock instruction, even if they are completely unrelated in the software, because lock instructions going to different memory locations still have to have a total order. So that's, I worry about the locality consequences when you go to hundreds of cores, and how sustainable that will be.
Okay, well, we share your concern. Okay, absolutely. I mean, I don't. No, I'm not sitting here saying that, well, we don't think about that. We put lots and lots of cycles into concerning ourselves about that. But no, at this point, this is the memory model, and this is the memory model going forward. Sir.
Does your memory model apply to AMD's processors?
Does Intel's work apply to AMD? AMD has recently come out with a very similar memory model. I think we pretty much independently came to the same conclusion. The only difference in their documentation that's substantive is that they specifically allow stuff that we allow through omission. Okay, I mean, we don't say you can't do it, so the rules are you can, and for some reason they feel obligated to actually say that you can do some things. So that's really the only difference. So if you code to this and decide to buy AMD processors, you'll be fine. Okay, I wouldn't worry about that. That's not an issue. But I would advise you to read the AMD manual yourself. But the one time I read it, it said, well, it's just what we're doing. Yes?
The AMD processors currently have a bug in their lock instructions, which don't actually do a memory fence.
They have a bug within their lock instructions that don't do a memory fence?
Yeah, the lock instructions of the AMD actually sometimes don't do a memory fence.
You may find this surprising, but Intel has had bugs in their processors also. we do it, but I think everybody agrees that it's a bug. I think AMD is actively, I'm sure, I can't speak for AMD, but if they want to stay in business, they're going to, just like us, they're going to be working on making sure that that's okay. I actually wasn't aware of that bug, but that's interesting stuff. We should publish it widely.
So the reason you didn't want to go for a more relaxed model with explicit fencing is because those fences weren't available on older processors?
I don't think that was the reason nearly as much as it would break code. Okay, if we had announced that we went to a weaker model and that locks weren't, didn't have a memory fence, for example, we felt that would break code. Obviously, it broke somebody's code, or it wouldn't have been noticed. So that was really the reason. We really couldn't start. We didn't have a clean plate like we had with the IPF, okay, where we could actually go in there and define whatever we thought was the current technology. We had to deal with legacy. And I think, if you look at the memory models got weaker and weaker and weaker. The Alpha and the PowerPC was weaker than x86, and the Alpha was weaker than the PowerPC. And I think that's, so people kept getting weaker, and now people are trying to use other techniques to go back to these to models like ours and try and make the legacy model work, but make it work faster. Just like we've done this for years. We've said, okay, we're going to keep the same ISA, but we're going to make it run as fast as a RISC machine. Okay, so this is not, it's not something we're unfamiliar with. Okay. Thank you.
Okay.